Hi, I'm Shaunak Halbe from the College of Engineering Pune, and this summer I'm participating as a RIS student at the Bot Intelligence Group under the guidance of Dr. Jean Ho, and I'm closely working with my mentor Ingrid Navarro. I'm here to present my project Reason and Act, which is a modular approach to vision and language navigation. I'll briefly explain the task of VLN. In VLN, given a natural language instruction to reach a goal, an agent must find the best sequence of high level actions that lead to the described goal. VLN makes certain strong assumptions. The most important among these is that the agent moves by snapping or jumping across discrete viewpoints that are distributed across the scene. This assumption makes the task quite different from the real world setting. To bring the task closer to the real world scenario, the Vision and Language Navigation in Continuous Environments or VLN-CE task was proposed. Here, based on the natural language instruction, the agent moves but by executing low level actions to reach the goal. The task of VLN-CE is quite challenging as the action sequences are much longer as compared to VLN, and there is a need to address imperfect actuation and localization. The current approaches to VLN-CE are end-to-end that perform perception, reasoning, low-level control, and other qualities in a single model. A task like VLN-CE, which is intrinsically hierarchical, requiring attention to detail at different levels, it is difficult to fit all of these requirements in a single model. Hence, we believe that a modular agent can help solve this task. Hence, we present a modular agent in the form of a global and local planner. We further divide the global planner into different components. The first among these is the perception and pre-processing component. Here we use a faster RCNN pre-trained on visual genome to extract bounding boxes from the RGB observations. We use a ResNet encoder to extract depth features from the depth images. The instructions are tokenized and embedded using LexMud tokenizer and its embedding layers. Coming to LexMut, we use LexMut heavily in our task for performing vision and language grounding. So the LexMut model is basically a transformer which was pre-trained on a series of multimodal tasks like VQA image captioning and many more. We use the LexMut model in the vision and language grounding module. We extract the last layer's outputs from the vision and language stream of LexMut to produce the grounded features. Additionally, we use a separate ResNet encoder to encode the depth features, and we employ cross-modal attention on top of these three different modalities. The cross-modal attention uses each of these features to attend over the other two features to finally produce a very strongly grounded feature vector. We pass this feature vector to the reasoning module. In the reasoning module, we task the agent to predict the object which is most relevant to the scene and to the supplied instruction. This is done. The ground truths for these objects are generated from a knowledge graph. We use a knowledge graph which was from the visual genome dataset, and we filter it based on the objects present in the Matterport simulator. The knowledge graph contains associations of different objects and regions. For example, if we consider the object television, it is often associated with the object wall and often is seen in a bedroom or a living room. We extract such associations from the knowledge graph, and we extract the objects from the instruction and from the visual observations. We match these extracted objects with the ones in the knowledge graph and pick the one that has the maximum association with the region that the agent is presently in, and we choose this object as a ground truth, and we make the model predict this predict this object in the reasoning module. Finally, the global planner generates a waypoint in terms of distance and heading relative to its current position. Such a waypoint is passed to the local planner, which executes a series of low-level actions to reach the goal. The local planner was trained separately from the global planner and uses proximal policy optimization. We for training the entire for the training the global planner, we use Dagger plus imitation learning. We use Dagger to generate the trajectories and imitation learning to learn them. We write our code in PyTorch, and all of this is based on the Habitat AI simulator. Now, but coming to our results, we perform a study where we compare the use of LexMod encoder as compared to the ResNet RNN encoder which was used in the baselines. We find that the LexMod plus CMA approach has good gains as compared to the ResNet RNN model. And we note here that the LexMod plus CMA model was trained on a subset of the data, and when trained on full data, we believe that the LexMod model will give even better results. Now we also compare the use of reasoning module and observe that the reasoning module offers gains that are around 5 to 6% more than without it. So this was also trained on a subset of the data, and we believe that training on the entire dataset will give even better results. Finally, I would like to thank my mentors for their guidance during my internship. I would also like to thank my sponsors for their support. And finally, I would like to thank Dr. John Dolan and Ms. Rachel Wilson for organizing this and allowing me to be a part of it. Thank you.